a 3-phase 50 Hz generator is rated at 500 MVA, 20 kV with XD double dash is equal to 0.2 per unit. It supplies a purely resistive load of 400 megawatts at 20 kV. The load is connected directly across the terminals of the generator. If all the 3 phases of the load are short-circuited simultaneously, find the initial symmetrical RMS current in the generator in per unit on a base of 500 MVA 20 kV. So it is given that all the 3 phases are short-circuited simultaneously. That means it's a symmetrical fault. Okay. Now it is also given that it is a purely resistive load. Okay, and the Thevenin's equivalent model that we discussed, that was when there was only reactance. Okay, we have ignored the resistance, right? So when there is a resistive part, it is better to go by the conventional path rather than using the Thevenin's theorem. Okay, so first we will draw the circuit. What is given? The generator has XD double dash, that is subtransient value, as 0.2 per unit. Okay, and internal subtransient voltage we are going to take like this. Now it is connected, the load is directly connected to the generator, right? That is also given in the question. So this is the load, it is purely resistive, so you can even draw a resistance here. Now the fault, it is occurring here. Okay, so then what will be the fault current? This is going to be EG double dash divided by JXD double dash. Okay, so here this point is going to be shorted with the ground, right? So this part will form a circuit, so the current through it is going to be this voltage divided by this reactance. We anyways know this XD double dash, we need to find out EG double dash. Since we are dealing with per unit values, we will have to set the base values also, right? So what are the base values that are given? It's already given that you have to take base 500 MVA and voltage base is 20 kilovolt. Okay, so you can write this out. The MVA base is 500 MVA and the base voltage is 20 kilovolt. Okay, and it is also given that the resistive load, it is 400 megawatt power it is taking at 20 kilovolt, right? So this voltage here, this is the pre-fault voltage. If you take, this is given to be 20 kilovolt. That means the what is the per unit value? This is going to be actual value by base value. So this is 1 per unit. Okay, so we now need to find out EG double dash in per unit. So we will consider the pre-fault condition for that, right? That is how we find out EG double dash. So this is, these values will be the subtransient values, and here you have the resistance. This is the pre-fault voltage and this will be the load current IL. Okay, so now if you apply KVL here, then what you are going to get? EG double dash is equal to VF plus IL JXD double dash. Okay, so now VF we know in per unit, XD double dash we know in per unit. So we will find IL, the load current in per unit. Okay, so IL per unit is equal to the actual value of IL divided by the base value of the current. So what will be the actual value? It is given that it is a purely resistive load which is delivering how much? 400 megawatts at a voltage of 20 kilovolt. But this is a 3-phase system, right? So here into root 3 will come. Okay, and what about the base value? This is going to be 500 MVA divided by root 3 into 20 kilovolt. So this will be 4 by 5, which is 0.8 per unit. So from here you can find out EG double dash. So this is equal to 1, VF is 1 plus IL is 0.8 into, see 0.8 angle is 0 degrees only. Why? Because VF and IL, they are in phase. Okay, So IL will be also 0 degrees. VF we are going to take as a reference usually, right? So 0.8 into J 0.2. Okay. So this you are going to get 1.013 angle 9.09 per unit. Once you know EG double dash, then you can find out the fault current from post fault circuit. What will be the post fault circuit? Simply short circuit. Okay. This is IF. This will be double dash. Okay. So the subtransient fault current, this is going to be 1.013 divided by, you can take the angle as well. If you want only magnitude, no need to take the angle, divided by J 0.2. Okay. So this you are going to get 5.064 angle minus 80.91 degrees. This is in per unit. Okay. Now we want the actual value, actual RMS value, right? So IF actual is equal to IF dash double dash per unit into the base value of current. Okay. So this is going to be 5.064 into 500 into 10 to the power 6 divided by root 3 into 20 into 10 cube. So this, if you calculate, you are going to get 73.09 kilo amperes. Okay, so this will be the fault current. The diagram shows a power station layout having two generators A and B connected to the 11 kilovolt buses, which are also fed through a reactor R. Okay. The reactances of A, B, C, D and R are in per unit on a common base MVA and kilovolt base. All the generated voltages in A, B and grid are each 1 per unit and assumed as in phase at the time of the fault. The steady state symmetrical fault current for a 3-phase fault on the 11 kilovolt feeders is. So first we will study the power station layout that is given. Okay, so this is the grid and it has a negligible source reactance. Okay, and this is transformer. C and D are transformers. Okay, so from 132 kilovolt to this bus is at 11 kilovolt. Right, this is also at 11 kilovolt. So both the transformers, they are voltage step down transformers. Okay, and they are having the same reactances as well. A and B are generators and their internal reactances are given. Okay. Now these are the feeders and these two buses, they are interconnected by a reactor which is having a reactance 0.1 per unit. Okay. And these are the feeders. Now the fault is occurring at one of the feeder here. Okay. Now we need to find out the symmetrical fault current. When they say symmetrical, it is a 3-phase fault, but 3-phase fault is also mentioned, right? So we have to find out the fault current for 3-phase fault. Now here the reactances of every equipment is known, right? For the grid it is negligible anyways. For the transformers, generators and the reactor, we have the reactances. Okay, so we will simply find out the Thevenin's reactance and then we can find out the fault current. Okay, and one more thing is they have given all of the information regarding the per unit values. What they gave? A, B and grid are each at 1 per unit voltage. Generated voltage is 1 per unit. Okay, and they are all in phase. That means angle is 0 degrees. So we will first try to draw the equivalent circuit. First we will take this bus as node 1, okay, and this bus as node 2, okay. So at bus 1, that is node 1, you have the fault, okay, and at this bus you also have this generator A. So we can first draw the generator. It will have the internal reactance J.2, okay, and this is internal generated voltage. Generated voltage is given as 1 per unit, right. So here you have this. Now this is node 1, and this is where the fault will occur. Next we will consider this reactor. Okay, so this reactor 0.1 per unit connected between 1 and 2 nodes. Okay, so we can draw here one reactor and we can name the other end as node 2. So this is 0.1, J 0.1 per unit. This is R. Here also you can name this as A. Okay. Next, what is given? You can next take the transformer. So node 1, all of them will be complete once we draw the transformer. Okay. So the transformer will be like this. We will take this as C, right? J 0.2. Now the other end of transformer is connected to the grid. Okay. So it will have a voltage 1 angle 0, and then the grid will again be connected to the ground, the other side of the grid, right? So here you can draw the internal voltage of the grid, and this again it will be connected to the ground. And next you have from node 2, you have drawn R, you need to draw D and B. So D is connected to the grid again, that means this point, right? So you can connect another reactance here, which is D J 0.2 per unit. Finally, from 2 to the ground you have another generator B. So J 0.2 per unit, and you have the internal voltage 1 angle 0 degrees. Okay. So now how we have to see the Thevenin's equivalent? We have to see from node 1, right? And also you have to short the internal voltages. Okay. So Thevenin's equivalent you can draw. This is A, J 0.2, and from here we are looking in, right? And here we have J 0.1. This is one reactance. This is another reactance, and these are both connected to the ground, right? And here lastly we have J 0.2. Okay. So here we can finally write the Thevenin's reactance. First you can see J 0.2 and J 0.2, these two are parallel to this entire combination, right? So here again these two are parallel, J 0.2, J 0.2, and this parallel combination is in series with this. Okay. So what you are going to get? J 0.2 parallel to J 0.2 parallel to a combination of J 0.1 plus J 0.2 parallel to J 0.2. Okay. So now this will be J 0.1. So 0.1 plus 0.1 you are going to get J 0.2. So totally you are going to get 3 reactances, each of reactance 0.2. So what will that be? J 0.2 by 3. So this is going to be J by 15 per unit. Okay. Then what will be the fault current? This is going to be 1 by XTH. So here we are only concerned with the magnitude, right? So this is going to be 15 per unit. Okay. So anyways, they have not given they said that it is on a common base and kVA, all the per unit values, but they didn't give the base values. Okay. So we will get the final answer in per unit. A 3-phase generator rated at 110 MVA 11 kV is connected through circuit breakers to a transformer. The generator is having direct access subtransient reactance XD double dash is equal to 19%, transient reactance XD dash is equal to 26%, and synchronous reactance is equal to 130%. The generator is operating at no load and rated voltage when a 3-phase short circuit fault occurs between the breakers and the transformer. The magnitude of initial symmetrical RMS current in breakers will be. So you can see it is given the initial symmetrical RMS current. Okay. So you have 3 different reactances here. Which one will you use depends on this word here, initial. Okay. So when it says initial, right after the fault. So when right after the fault, what will be the reactance? The subtransient reactance. So we have to take 19%. Okay. Others are all just to confuse you. Okay. Now it is given that the short circuit fault will be in between the breakers and transformer. Okay. Effectively the transformer is being short circuited, right. So here you will have the generator only, and here you have the transformer connected. So if you take the reactance, some reactance that is anyways not given, here the fault is going to occur. Circuit breaker is nothing but it's like a switch, right. So now we have to find out the fault current. What will that be? IF double dash, because they are saying initial. So this is going to be what? 1 angle 0 degrees divided by JXD double dash. Okay, so why did we take 1 angle 0 here? The generator is at no load, right. So whatever voltage will be available here, the same will be the internal voltage. Okay, so that we will anyways take as 1 per unit. Okay, so this is going to be 1, only the magnitude if you are going to take. 1 divided by 19% is 0.19. Okay, so here you are going to get 5.26 per unit. Remember, we are taking only the magnitude here. If you want, you can take the phase as well. Okay, so but we are only concerned with the magnitude. It's given in the question itself. Okay, so now this is the per unit value. Now the phase values, the base values, are they given? It is given in the question. Rated at 110 MVA and 11 kilovolt. Okay, so here you can take the base current will be equal to the MVA, so or you can write into 10 to the power 6 divided by root 3 into 11 kilovolt. Okay, so this you are going to get 5773.5 ampere. So what will be the actual fault current? This is per unit. Okay, so per unit value into the base current. So here you are going to get 5.26 into 5773.5. So this you are going to get 30.37 kilo amperes.